The Hubble Space Telescope was deployed in 1990, a model for the velocity of the shuttle from liftoff at t equals 2 to when the rocket boosters were jettisoned at t equals 126 seconds is given by v of t equals all of that feet per second. Using this model, estimate the maximum and minimum values of the acceleration of the shuttle between liftoff and jettisoning of the boosters. Now, this is a scenario where we can use the closed interval method because we have a continuous function on a closed interval. So that's great. But why we would want to use this is because when NASA or SpaceX or anyone is sending something into outer space, they need to understand what the range of accelerations is going to be to determine how secure everything on board is going to be. Of course, if the acceleration is too much for the rocket to handle, then things are going to get destroyed. So this is a really important application of calculus here. Now, there is one thing I want to point out. We have been given a velocity function, but we want the maximum and minimum values of the acceleration. So before we do anything else, we need to take the derivative of this to find the acceleration function. So the acceleration as a function of t is going to be the derivative of the velocity as a function of t. And so we need to differentiate one term at a time. The derivative of t cubed is 3t squared. So we're going to have to multiply that coefficient by 3 and then stick a t squared after it. So that's going to be 0.003906 t squared. Then we have minus the derivative of this next term, which has a t squared in it. The derivative of t squared is 2t, so we're going to have to multiply this coefficient by 2. That's going to be 0.18058, and then t. And then the derivative of the linear term is just the coefficient, 23.61, and the derivative of the constant term is 0. So this is the acceleration function. Note that it is a continuous function, and we're looking at a closed interval from 0 to 126 seconds. So we can use the closed interval method. To do that, we're going to need to differentiate the acceleration function so that we can find any possible critical numbers. Now, the derivative of t squared is 2t, so we're going to have to multiply this coefficient by 2. That's going to be 0.007812, and then t. And then the derivative of a linear term is just the coefficient, so 0.18058. So that is our derivative. There is nowhere where it's undefined, but it is equal to 0 somewhere, so we need to solve that. We can solve this by adding the constant term to both sides. That's going to give us 0.007812t equals positive 0.18058. And if we divide both sides by the coefficient on that t, we get an answer that's approximately equal to 23.1157 for our value here. And that is our only critical number. So we're going to have to evaluate our acceleration at the critical number, which is approximately 23.1157, as well as at the end points. So that's going to be 0 and 126. And I'm going to use calculators here. Well, we don't need to use a calculator for a of 0, because if we plug in 0 for our acceleration function, the first two terms go away, and we're just left with the constant term, which is 23.61. But for the other two, I'm going to use a calculator. And I get, for our critical number of around 23, a value of 21.5227. And then for our other endpoint of 126, I get 62.8673. Now, all of these are accelerations, and we're dealing with feet and seconds. If it was velocity, that is feet per second, but acceleration here is going to be measured in feet per second squared. So all of these are feet per second squared. And we wanted to know the maximum and minimum values. The maximum is certainly coming from 126. So we have a max acceleration of 62.8673 feet per second squared at time t equals 126. And we have a minimum acceleration of 21.5227 feet per second squared at time t approximately equal to 23.1157. And NASA or SpaceX, if we're looking at an example today, would use this information to determine how much stress all of the things on that telescope and on that rocket are going to be undergoing, and to make sure that everything is stable for that launch.